Hey friends, what we're going to do in this video is we're going to talk about increasing and decreasing functions again, but this time we're going to determine these regions of increase and decrease algebraically. So essentially, what are we going to do when we don't have the graph given to us? All right, always algebraically means a little bit more work, but it's actually not that bad. So remember from the last video, in general, if a function, the derivative of a function is negative, the original function is decreasing. If the derivative is greater than 0, the original function is increasing. And if the derivative of the function is equal to 0, then the original function is neither increasing nor decreasing. Okay, and again, these all relate back to the slopes of the tangent lines. Okay, that's what the other thing I want you to think about here. Visually, the derivative is all these slopes of these tangent lines. Now, the interesting part of this is this last part right here, where f prime at x is equal to 0. What we saw in the last video is that's a really, really, really important thing that's happening here. Okay, let's consider the graph of the absolute value. So I know the absolute value function looks something like this. It's this really sharp looking V, just like that. Okay, so what I know visually by looking at this is I can tell that I'm increasing. My slopes of my tangent lines are positive. I'm increasing from 0 to infinity. I'm decreasing where the slopes of my tangent lines are negative, from negative infinity to 0. And right here, I'm going to switch pen color to maybe pink. Right here, at 0, I'm neither increasing nor decreasing. But what I really want to point out here is my derivative right here does not exist. Okay? And one of the reasons why you could think of it as not existing is think of how many tangent lines I could draw at that moment. I could actually draw an infinite amount of tangent lines. That's one way to think of it. So definitely at 0 is the important part because that breaks up where I'm looking for increase or decrease. Okay, so this is the first thing we're always going to want to find is the moment, the x value that our function goes from increasing to decreasing. So what we'll do is we're going to find the intervals in increase and decrease, and we'll look where our function has a max or a min, or where the function may not exist. And to do that, we're going to find what's known as the critical number. And we're going to call it C. It's in our domain of our function such that, this is the really important part, either the derivative is equal to 0 or the derivative does not exist, just like on the absolute value. Where we get is a really important theorem by a famous mathematician named Fermat, who says that if the function f has a local max or local min, then it occurs at a critical number. Okay, so let's go and find these critical numbers. This is the first thing you're always going to do when you go to find intervals of increase and decrease. So to find our critical number, and Fermat's got some really, I mean, he was a famous mathematician, and there's something known as Fermat's last theorem that you can look up that caused mathematicians worlds of angst and was just solved, I don't know, a couple decades ago. A big prize was awarded for it. Who knew, eh? Okay, we're going to find our critical theorem. Look at what happens when I'm talking and writing at the same time. Should not try that, hey? Let's find our critical numbers, friends. So our critical numbers are when our derivative is equal to 0 or where the derivative does not exist. So, and take the derivative. So f prime at x, take the derivative of 3, 0, 7 minus 6x. So to find our critical numbers, what I'm going to do is I'm going to set my derivative equal to 0 and solve for x. So I have a critical number at 7 over 6. That's where the derivative is equal to 0. What about where the derivative doesn't exist? Well, I don't have to worry about that because my derivative is a linear function. It exists everywhere. So there's our only critical number. X is equal to 7/6. Okay, how does that help us? Well, now to find the intervals of increase and decrease, what I'm going to do is I'm just going to make a number line. And I'm going to put my critical number right there because I know something's happening at 7/6. So that's where my derivative is equal to 0. That means my function's neither increasing or decreasing at that moment. So I'm going to have potentially a max or a min there. So now all I do is I pick a test point. So I'm going to pick a number smaller than 7/6, like 0. I'm going to pick a number bigger than 7/6, like 100. And what I'm going to do is I'm going to sub these numbers back into my derivative. So when I sub in 0, I get 7 minus 6 times 0, so I get 7. I don't even care about the number, friends. I care that it's positive 7, right? And when I stick in a hundy, I get 7 minus 6 hundy. That's negative. So what does this tell me? Look at, we just changed going from increasing to decreasing. So right here on this region, I'm increasing because the slopes of my tangent lines are positive. I'm increasing from negative infinity to 7/6, and I do not include 7/6. Here, I'm decreasing. And I'm decreasing from 7/6 to positive infinity. That's it. Hey, not bad. So again, we find that critical number, we do test points on either side, and we see what happens. Just remember, a critical number does not guarantee a max or a min. It says, based on Fermat's theorem, if a max or a min exists, it would have to occur there, but it doesn't guarantee it. Okay, let's try a slightly more complicated one. Find the intervals of increase and decrease where f at x is equal to x divided by x squared minus 1. Okay, so I'm going to take the derivative here. So sometimes taking the derivative is the longest part. We'll use quotient rule here. So bottom times the derivative of the top minus the top times the derivative of the bottom. Yes, I should be saying numerator and denominator. I'm a bad teacher, I know. Don't yell at me. Okay, bottom squared. Simplify your numerator. So look at all these things that you were asked to do earlier in the course. And now you see a little bit maybe purpose to them, right? Or more purpose to them. And simplify it one more time. So in the numerator, I get, what do we get? Negative x squared minus 1 over x squared minus 1 over x squared minus 1 all squared. Okay, so now our critical numbers. So critical numbers. Again, I like to write this out every time so I don't forget. That's where my derivative is equal to 0 or the derivative does not exist. Okay, so let's go set our derivative equal to 0. Can do. Just like that. All right, let's first look at where we don't exist. Well, we don't exist in the denominator here because we could have the potential for division by 0. So we don't exist when x is equal to -1 and x is equal to +1. Okay, so we'll keep that in mind. So there's two critical numbers right there. Now we keep solving. So I multiply both sides by the denominator and I end up with that. And I start solving. Well, I add x squared to both sides. X squared is equal to -1. Well, we can do that, but it's an imaginary or complex number. We don't want to do that. Nothing to worry about there. So our only critical numbers are -1 and 1. Okay, so now we're going to do our sign analysis. So I take my critical numbers and I put them on a number line, just like that. And then I'm going to pick some test points. So to the left of -1, smaller than -1, negative 100, in between negative and 1, 0, bigger than 1, 100. Now, what I'm going to do is I'm going to sub my test points into here. Now, what I want you to notice is in the denominator, it's always going to be positive in the denominator because we're squaring, right? So I know no matter what, the denominator will be positive. Nothing to worry about then. In the numerator, I sub in negative 100. Negative 100 squared is positive, but times a negative would make it negative. So this will be negative. I sub in 0. Again, the denominator will be positive. When I sub in 0, I'm going to get 0 minus 1, which is negative 1. Okay. And then on the last one, I sub in 100. And what I'm going to get is I'm going to get 100 squared, but negative because the negative again, and minus, look at that, I get another negative. What the heck is going on with this thing, right? Like there's something interesting happening here. Maybe it wasn't what you were expecting. What does this tell us? It's negative everywhere. So what I know is we're decreasing on the intervals saying negative infinity, and I didn't write it, negative infinity to negative 1, union, negative 1 to 1, union, 1 to, I did it again, infinity. Interesting. It's never increasing. This function's always decreasing. Well, what's happening at negative 1 and 1? Well, if you want to think about what's happening at negative 1 and 1, let's go back to our original function. Those would be our non-permissible values. Those would be vertical asymptotes. So what I can already do, friends, is take a quick shot at graphing this thing. Now, I'm not saying it's perfect, but by the end of the unit, you will be able to graph this thing perfectly without a graphing calculator. How cool is that? So I've got a vertical asymptote at negative 1, a vertical asymptote at positive 1, and this function is always decreasing. Well, I know a little bit about rational functions. This thing here is going to look like this. It's always decreasing. Now, you don't know how to do what I just did yet. Okay, that's just experience, which you'll have by the end of the unit. But now I want to check my work because, hey, I've got a graphing calculator probably still from 30-1. So let's check it out. So at this point, I pick up my graphing calculator and I sub it in, my function, and look at, there it is. That function is always decreasing. The slopes of the tangent lines are always negative. Pretty cool, hey? Okay, so again, when you're doing this in your homework, you're looking for your critical numbers, and your critical numbers are where your derivative is equal to 0 or does not equal to 0. Then do a sign analysis chart, and you can figure out everything from there. Okay, friends, I hope that helps. See you another time.